Okay, let's do a little share of my screen. Get your slideshow going. Okay, so this is the mechanism I was talking about for the citric acid cycle. It's really the only mechanism we're going to look at in some detail. This is the first reaction. We got pyruvate turned into acetyl-CoA, and acetyl-CoA goes into the citric acid cycle. Again, 4 carbons plus 2 carbons gives us our 6 carbons. And ultimately, we lose 2 carboxylic acids as this comes back around to oxaloacetate. The reaction here is catalyzed by citrate synthase. And you can see that we have a OH being replaced basically by an SH. Okay, so this is a view of citrate synthase. And this is the dimer of the enzyme, and so it combined 2 substrate molecules in these active sites, and look what happens when this thing binds. We talked about induced fit. Look how that clamps down upon substrate binding. That cleft is just gone. It just snaps down. This is a citrate synthase that's a little different. This is from a bacterium that is found in hot springs, and it's very similar, but notice that it's got these disulfide bonds here. These help to stabilize these mobile loops in the middle. It helps it tolerate high temperature without denaturing. All right, so first step in this mechanism, this is right from your book, so you can take a look at this in your book. I just sort of pieced it out a little bit. So remember chymotrypsin had that S, D, and H. Here we've got a D and an H, but it's a little different here. The aspartate and the histidine are not going to directly interact with each other. They're going to interact with different sides of the substrate. And remember, this reaction is not cleavage of a bond. It's the reverse, really, where we're making a bond. And if you look to see where it's happening, you see basically you've got a situation where this carbon here, okay, ends up binding to this carbon here at the carbonyl. So you got a nucleophile with this carbon, an electrophile with this carbon. So it adds it right in there, okay? But the attack is not cleavage of this bond. That's not cleavage of the, like the peptide bond cleavages for chymotrypsin. It's actually going to be attack one away. So here's our aspartate, here's our histidine. The aspartate is deprotonated, the histidine here. Notice it's got 1 proton here, but it doesn't here. So it's actually neutral, not plus charged. That's important too. So the pKa comes into play once again. Oxaloacetate and acetyl-CoA both have to come in and bind to the enzyme. So here's the acetyl-CoA first. You can see this carbonyl oxygen is in close proximity to the hydrogen. The carbonyl is not what's attacked here, right? Because we're not going to break this bond. What we're going to do is break this bond up here. And here's our very negatively charged oxaloacetate, those COO minuses in there. There's some basic amino acids and a metal ion that help to stabilize that oxaloacetate. So the O minus actually attacks the H on our acetyl-CoA. The H comes off as an H plus, right? Because this is an O minus, so we get an OH forming here. That means that there's a lone pair left behind in this carbon, which flips up for the double bond, and then that forces this O minus to go up here. This carbonyl swings up, just like we saw kind of with chymotrypsin. It's just that it's happening a carbon away. It's not going to break this bond here. Notice this histidine is in really nice position then to stabilize that O minus. Look at that nice hydrogen bond there. When the O minus reforms, it's going to flip down here, and then this becomes pentavalent, has to break one of those bonds. And in this case, instead of breaking the bond with the carbonyl and the sulfur, like we would see with a peptide bond breaking, we've got this adjacent double bond, which is going to act as a nucleophile for the best electrophile over here. Now we have a bunch of electrophiles over here, right? We got this carbon, this carbon, this carbon. And of those, right, these carboxyl carbons are actually more electropositive. But this carbonyl one here is the one that's in close proximity with the binding, and the basic amino acids here and the metal ion over here are helping to stabilize and get these COO minuses out of the way. So this transition state ends up with a bond going all the way from histidine to the O minus. When that swings down, the bond between to the histidine is broken, but you've still got association between these guys forming. So that's your transition state. And then we have a situation where this bond forming with this gives you an O minus on this carbonyl, and that ends up getting protonated to an OH. If this goes to an O minus and then flips back down, this whole reaction can basically go in reverse. But once this has an OH here, it's much more stable and less likely to break this bond again. So now we've pretty much got our product. We've got this citrate forming here. The only thing is that this needs to be an O minus on this end. We need to get rid of that coenzyme A. So the next thing that happens is there's a water molecule that comes in there, and that oxygen of the water molecule attacks our carbonyl. This gives us a O minus here. Again, helps having that histidine there. Attached here then is an OH2, and one of those H's ends up going with the sulfur of the coenzyme A. So you have HSCOA, or sometimes you see this written as COSH, COASH, and then release of this other one as an H+. So this second phase of this reaction, you've got a proton coming in and a proton coming off. This is basically acid catalysis, right? Now our citrate is fully formed. Everything's all set, except this aspartate is still protonated, and so the enzyme doesn't work anymore. So the last thing that has to happen in order for this to regenerate is you have to lose another H+ before the aspartate's ready to react again. Okay? So take a close look at that mechanism. Make sure you can recapitulate most of that like we did with chymotrypsin. It's the only mechanism you're going to need to know for Krebs cycle. So you want to make sure you can identify those amino acids and the nucleophilic attacks and explain what's happening where. Okay? All right. I'll see some of you guys Tuesday, some of you guys Wednesday. Go, I don't know, go build a snowman.